Good evening or good afternoon to Dr. Andres, to our workshop, 3 days workshop. And Dr. Ondřej Bojar is a lead scientist in the field of machine translation in Czech Republic. He works as a professor at the Institute of Formal and Applied Linguistics at Czech University. Machine translation has been in the center of his research interest since 2005, early in his PhD studies. He has been regularly participating and since 2013 organizing WMT tags with specific focus on translations into Czech. His system has dominated English-Czech translation in the years 2013 to 2015 before deep learning and neural network fundamentally changed the field. He has published more than 300 research articles, books, conference papers, and his main focus now is a little broader and entails machine learning in general with explicit aims toward the meaning of representation, natural language understanding, including speech, and also little about generative AI also. Thank you, Dr. Andres. Now session is yours. Thank you very much.
Yeah, thank you for the nice introduction. And I'm looking forward to the presentation. I understand that it's close to evening or late afternoon in India, but you are connecting from all around the world. So yeah, I'm still joining from Prague. I can offer a quick peek. Hopefully you see the steeple of St. Nicholas Church. I don't know if that is visible. This is where this is where Shantipriya spent some time. I'm really happy that this connection between Prague, the Charles University, the Institute of Formal and Applied Linguistics, and India works very well through Shantipriya. And other colleagues, and I'm happy that I'll be able to present my experience with Czech, because Czech is a small language. We are only 10 million people, and the language is over-engineered, as I keep saying, because it was almost lost when we were part of the Austrian Empire. All the educated people spoke only German, and Latin was like for the scholarly purposes, and it was only people in villages who kind of maintained the language, and only then some restoration of the language came, and the linguists found it interesting, and they formalized the language following the very complex Latin grammatical rules, but Czech is a Slavic language, so it was like a mix of approaches, and it was after this restoration, or during this restoration, it was really sometimes recreated. Many words were invented by these linguists, so it's over-engineered. It's designed to the likeliness, to the enjoyment of linguists rather than to the practical uses, and it has some consequences on natural language processing of that. And I had the luck of working on this language and seeing the language being covered from not nothing. There is a long tradition in linguistic analysis of Czech, but in machine translation from very poor translation quality beginnings to the level of human quality translation. And the presentation is about this and about some lessons I learned throughout these few years. So I hope that now you are able to see my slides.
Yes.
Yeah. And I would like to invite everybody to ask questions even during the presentation, because it can easily happen to me that I'll be talking for too long. So if you have any questions, I suggest that you simply shout if that's not a problem for the recording of this session. Yeah, hide floating panels. Okay, so what I would like to talk about today is a very quick overview of machine translation approaches to it, and my personal involvement in that, but it will be very short. I think it's necessary to do this because the workshop as such is on large language models and natural language processing in general, and machine translation is only one task of that. So I need to clarify why I think it's like relevant, and what is why this example of natural language processing is relevant for all of you. And I'll then talk about data. This is the very basic ingredient that you must have, and if you don't have it, you don't have any chance to have any good performance in your language. And I'll mention two selected like quality jumps that we saw in English to Czech translation. I could have added one or two more, but I just decided for these two. One of them is something which we call reverse self-training, and these days it is known under the term back translation. And then I'll talk about some training magic that my colleague Martin Popel has found out and used in transformer training. And with this training magic, Martin Popel actually reached the translation quality comparable to humans. So that's the question that I will ask around the middle of the presentation time. And then I'll definitely have to stress again what I keep stressing in all my recent presentations, and that is big caveats on evaluation. So I have some views on that, and I'm sure that you have yours as well. I think the whole discipline, the whole area of natural language processing needs serious discipline. The discipline needs discipline in evaluation. And the companies who are making great profits on large language models are dismantling this discipline and are like confusing even ourselves, researchers, about what the models are capable of. So we need to keep stand and stick to our old methods and be sure that we attribute the gains we see to good reasons, and not and that we are not just fooled by some data overlaps. So that will be the second part. Several cases where some misinterpretation of results can easily happen. But let's start with approaches to machine translation. I hope that the triangle of machine translation still remains in the active minds of researchers. We have some source text and we have some desired target language that we would like this text to be translated into. And it was called direct translation if you proceeded just from the sequence of words to the sequence of words. And when I started learning this, I graduated from my high school in 1997. So then like 5 years of master studies, or around 2004, 5, I started looking at machine translation. And back then it was still like conceivable, but some people did believe in that and some people did not. I did not. It was conceivable to think that there would be some interlingua and that we would follow the traditional linguistic analysis and the pipeline of or this set of layers of language description to get closer to the interlingua, to some language independent representation of the meaning of the sentence, and then to generate the target language. And this approach of analysis, transfer, and synthesis was promising because the transfer is definitely easier if you move to some more abstract representation. And in particular, as you will see later, Czech is very rich in morphology, and I believe Odia and other Indian languages are also equally rich. This transfer-based approach allows people to abstract away the complex morphology when doing the translation, and it's only the target language specific components that handle that complexity, which is very useful. The sad truth about this analysis, transfer, and synthesis, as depicted or illustrated in this triangle, is that the path from the source to target is maybe shorter here in the transfer part, but it's longer overall. So you have to develop the models that do the analysis, and you have to do the transfer accordingly, and then you have to develop the models for the generation. And along this pipeline, the errors typically accumulate. So in the end, this transfer-based approach has always been lagging behind the forms of direct translations. And these days, with neural MT, direct translation is like the standard thing. There's what we see as some intermediate representations are the hidden representations in the layers of neural networks. And yes, there are papers that see an interlingua there, but it's still not quite explained, right? So when I started, it was still a competition between the direct approaches and the transfer-based approaches, and it was actually best to combine all of them because they complemented each other with the tendency to make errors here or there. Yeah. So as a reminder, machine translation started with some rule-based approaches, and then it slowly got to example-based, where there were no longer smallish rules, but people were collecting existing translations, and they were searching for similar translations in these collections when a new sentence came to be translated. This example-based machine translation is already relying on the data. And then the statistical approach is fully relying on the training data. And it was the complexity of the models that was gradually improved and made the models more adequate. So the first approach is translated words for words. Phrase-based MT was something where I contributed personally, and for a decade this was the dominant approach. And at the same time, I was trying to plug in the syntax-based approaches, but I'm totally going to skip these because it was always too tedious to put them in, and the gains were good, but I would not say that they were worth the effort behind that. And then neural MT came kind of like as a bus coming from the side that you didn't expect, and it changed the practice a lot. But we were still benefiting from the data that we collected. And then within a neural MT, transformer has again made a big leap. So that's for people who are not aware of machine translation as a field. And I would like to bring up some old or even ancient, it's from the last millennium, citations that relate to the statistical approach to machine translation. And the first one comes from Warren Weaver, and he portrays translation as a decipherment problem. So you have text written in some foreign language, and you pretend that the text is actually written in the language that you understand, but it was through some code or noise. It just happened to be expressed in the wrong language, and you are going to strip off this code. And this is the statistical approach, which is not concerned with the meaning of the or it is, but it's like only in some hidden way. The meaning of the sentence. Very famous linguist Noam Chomsky is opposed to the idea of statistical approach by saying that the notion of probability of a sentence is an entirely useless one under any known interpretation of this term. And to add more to this hatred, but there's no real hatred between back then the statisticians versus linguists. Fred Jelinek, a former leader of the CSLP group at Johns Hopkins University, and born in Czech, sometimes visiting UFAL and working at UFAL as well, and the author of the IBM translation system, a very successful one, and speech recognition system, is attributed this quote: "Every time I fire a linguist, the accuracy goes up." And this is like exaggerating the tension. So what I like better is the citation from Professor Hermann Ney from RWTH Aachen University, a very strong group in machine translation. And he's originally a physicist, but still he likes the combined view. So he says that machine translation has to rely on linguistic modeling and statistical decision theory. So this is the best view I would adopt, that linguists bring the inspiration and ideas, and it's the statistical decision theory which should refocus the model and our working in this area towards the frequent phenomena, so that we solve the common cases better and first. Let's talk about data, because the data are the basis of everything. So when I started working on machine translation between Czech and English, there was really no data. And I would like to, only a very little collection of that. And I would like to highlight that yes, it does take time, but it is an effort which definitely pays itself off. And I'm happy that my colleagues in India, such as Shantipriya Farida, know this very well. So I'm happy that you are working hard on collecting data for your languages. This is the first step to have your language covered by language technologies. So what we had in 2006 when we were developing the first or second version of the Czech corpus were some legal texts which were available because the European Union we have joined the European Union just 2 years before that, and we already had some of the legal texts translated into Czech. Then there were some small collections of stories. There was the Reader's Digest journal that was qualitatively or were well translated to Czech, and there was also some collection of ebooks in Project Gutenberg. These were in English, and in Paměť CZ, and also a small corpus from the Faculty of Arts. They were available in Czech, so we could put them together. And there was this Project Syndicate, which still runs. It's news commentaries that are produced by journalists, kind of for journalists and for fun. So it's high quality texts, and they were translated to a number of languages. And then we had also user supplied data, which was Czech localization of open source project. And a company, one company also tried to translate the Wikipedia with their very poor machine translation system, but the users were then revising these. So that was another source of inputs. And I would like to highlight that whatever you can get, do get it for your language of interest or language pairs of interest. This is kind of an indication what the official sources, such as the legalese, can offer, 2/3 of the volume, versus what the user community can provide, which is at most like 10% or 15% of the data what we had back then. And I would like to highlight that the community supply data is often of good quality. What we saw in the Navajo project, the project where people were correcting the very poor output of machine translated Wikipedia, we saw 70% of flawless translations and 4.5% of almost flawless translations. So this is good. Of course, you would need to select these, which is not always the easy part. And there was only 2.7% of vandalism, and this was anonymous contribution. So that's a nice nice situation. And I think a similar proportions can be expected also in other languages. So it is worthwhile to ask users to do something even for free. And if the users do it in some registered way, such as in the open source community, where they are not anonymous and they are contributing to localizations of software, the quality is even better. It's almost professional quality, but because of the domain, it's not so useful for long text or full sentence translations. Additionally, in addition to these community-based translations and professional translations that I have talked about so far, we also had some proprietary data which we really couldn't use, and it amounted to 20% of our volume. And what we also had was the subtitles. I guess this is also the case for Odia, that people are very much interested in watching movies, and they contribute to large collections of movie subtitles. And in our case, it was 40% of the data. And I call it community translations of proprietary text because legally speaking, when you're watching a movie, even if it has subtitles in English or so, you are not allowed to translate the subtitles and translate the movie. There's copyright restrictions on this. So this is like copyright problematic content, but it's extremely valuable. So I just want to highlight that there is like two worlds: the world where you want to get the best performance, and the world where you really carefully obey some copyright restrictions. And yeah. To put this into the practical context, I have this plot which shows the old Cheng in 2008. It has this large green proportion of professional translation of something which I called in-domain. I had two test sets. Back then, news translation was the in-domain translation, and I forgot what was the other, but it was like different style of text. And for in-domain, I had this proportion of the professional translation. I had community supplied translation with proper copyright correctly cleared. That was not related to the domain, and it was very, very small. Then I had out-of-domain professional translation, which was not that's it. And then I had the subtitles where it was community supplied, and the copyright was unclear. And you see that the professional in-domain was about the same size as the subtitles. And this plot documents how machine translation, phrase-based system, an old one, gets better and better as you use more and more of this data. So there are two scales along which I could measure that: the BLE score, which is a very rough approximation of the translation quality, and the out-of-vocabulary rate, so untranslated words. And if you use only the community supplied clean, copyright clean data, you will get very poor quality in terms of BLE score, and also lots of missing unknown words. If you include the community supplied translation of subtitles, the out-of-vocabulary rate drops, so you get translations of many words, but it's out of domain, it's subtitles versus news texts, so you don't get good translation quality. If you use just the professional translated text, but out of domain, it's not much better. And if you use all but the in-domain data, you get the best coverage, but still the BLE score is not good. If you have good professionally translated text in domain of your interest, then you get maybe some words not translated, but best translation quality, and this is by a big margin. So that's one lesson to learn. You can then combine these sources with the professional translations out of domain. This will give you better coverage of words, but only negligible improvement in translation quality. And if you put all together, again, more words covered, but slight decrease in translation quality. The picture is somewhat different if you are translating out of your domain. Out of your domain, of course, the coverage is worse, the BLE scores are worse, and the short message is that the more you combine, the better you are off in both coverage of words as well as the overall quality. So if you know your domain and you have the capacity to produce the data, the professionally translated data, just focus on that, and that's the best you can do. But if your system is expected to process anything, if you don't know the specific domain, throw in everything. The idea is that instead of distinguishing domains, whatever, just collect whatever you can get. And I'm very confident that the same situation applies to any natural language processing systems. So not just to machine translation, but any like LLMs doing whatever tasks with their texts. If you can cover these tasks with training data relevant for the tasks, do so and focus only on that. If you are someone who runs an LLM for any purpose and you don't know the particular purpose that the users will then pick up, collect everything and throw everything in, and that will be the best. That will give you the best performance across the board. So this is the history. And again, I would like to stress this, even if your language is small, invest the effort into collecting the data. We did this over a number of years. So it was like 10 years to make the size of Czech not 100 times bigger, but 60 times bigger. And then we kept like switching between two phases. It was always like grow the corpus, clean the corpus, grow the corpus, clean the corpus. So that's what you can see in these different papers. There was always sometimes focus on adding more collections into that, and sometimes on filtering. And then the last version of Czech is 2.0, which contains about half or more than half of the text created by machine. So synthetic data is also definitely the way to go. But you need to be absolutely careful how to use that. How do you use the data then? Because if you use it in like forward direction and not backward direction, you are very likely to introduce biases, and you are going to mimic the system that created the synthetic data. Yeah. So one thing that I would absolutely like to highlight, and I didn't show any single sentence in Czech so far, and it would be of little use to you anyway, is data normalization. Aside from the Czech corpora, we also developed some Indian corpora with our Indian colleagues. And the first language, the first Indic language that we focused on was Hindi. So this is Devanagari. I don't know if all of you can read the script or none of you. I'm not sure. But when developing this Hindan Corp, the Hindi-English corpus at our institute, I was not able to read Devanagari at all. Some of my colleagues were, and they noticed that there is a lot of different orthography conventions, to put it nicely, and the word standards in Devanagari can be or was written in these three different forms. So for the machine, it is of course three different tokens, and it has to learn separately the meaning of this word, even though in all cases it should be just the word standard. So it really pays off to look at the data and carefully browse it in word by word, so to say, and normalize away all the distinctions which are unimportant for your application. This is definitely going to help you. So I've just talked to a student of mine, and he said, I would like to focus on translation between two Indic languages, but unfortunately I understand I can read the script only of the target one and not the source one. So the source one is Hindi. And instead of relying on machine translation tools, which in his case actually don't work because it's low resource languages in both cases, I recommend something much simpler. We are developers, so we should proceed with the with the low level representations of things. And when developing this corpus between Hindi and English, I needed to see and often edit actual characters. I was not interested in some presentation to the end users. So it was very important for me to be absolutely sure that the underlying bytes are the same. Or characters are the same. And because I couldn't read Devanagari myself, and of course the terminal windows in Linux operating system are also displaying the characters badly very often, I developed a simple thing. I Romanized Devanagari in a reversible way. So when the input was like, I want to see, and then I'm sorry, I cannot read Devanagari, this thing, my simple script, which you can download from here, converts this Devanagari script to Latin, possibly with some accents, because there are more letters in Devanagari than what the English Latin alphabet offers. And then suddenly, if you map it like letter by letter, then you can read it. I want to see Taj Mahal. So now I know what the sentence is about. And this very stupid and linguistically inadequate transformation still allows you as a developer to look at the data. And it's absolutely vital to look at the data, because then if I did this conversion with the standards word in its three different forms, I would notice that the spelling differs, and I would normalize it away. The romanization is not done according to some linguistic standards, as said, but it's done to offer one-to-one mapping there and back. So I can actually run the same script with some inverse flag, and it will convert back this Taj Mahal in this strange Latin notation to the original Devanagari. And this is done because the script contains letter by letter mapping. And this letter by letter mapping is sometimes unmotivated, and sometimes it is very poorly motivated. I have no idea what Chandra, the accent on O, looks like in Devanagari. So I selected a different accent. And for me as a developer, distorting what Chandra is not a problem. What is the important thing is that I'm able to distinguish whether there was a Chandra on the letter or not. And I immediately see that maybe in part of my collection, the accents got lost. If this happens, then suddenly you are kind of halving your data. In one of our experiments with Romanian, we were developing a system between English and Romanian, and we only later figured out that half of the Romanian data has lost its accents, and the system was learning two versions of Romanian, accented Romanian and non-accented Romanian. So Romanian is written in Latin, and we could see that immediately. But if some such simplification along the processing pipelines happens to your language written in script, which is hard to read for you, it's likely that you will not notice. In the Romanized version, which you can create the mapping for, you will notice. So the main lesson to learn so far is that you should collect the data, you should look at it, and you should be very careful to all the details. And if you don't see the details, you should use very low-level and simple tools to allow you to see the details. Yeah. So now let me talk about, if there are any questions, I was clear about this. Please just shout. Yeah. So I'll now move on to two selected topics in English-to-Czech translation. And the first one is addressing the morphological richness, because I think it's also relevant for your language. Czech, as said at the beginning in my introduction, is kind of over-engineered. We have a very rich morphological system. Our declination tables contain or describe 7 cases, 4 genders and 3 numbers for nouns and adjectives. And our verbs have also many categories: gender, number, aspect, and other things. So when you're translating a sentence from English, such as "I saw 2 green striped cats," the machine translation system is facing not only the ambiguity that this saw could be a chainsaw, or it could be the past tense of the verb see, but it also faces, in the target language only, the choice if you have like a complex noun phrase. So it's very difficult for the phrase-based system. It was very difficult to select which the combination of words it should use. you should also consider this morphological richness in contrast with your data. So, for example, the particle word kneecaps, which can be very important for your domain if it's a medical text, has all these morphological forms. And kneecaps in Czech is called češky. Right, so it's incidentally also a word which has quite a few accents on the letters, but that's just a coincidence. And if your parallel corpus is very small, just 50,000 sentence pairs, then you will be lucky to see the nominative of this particular word. But the phrase-based system was unable to produce any word forms it did not see in the training data. So a phrase-based system trained on 50,000 of sentence pairs was maybe able to translate češky, but only in the nominative case, not in any other cases. The problem of rich morphology is that the Zipf's law applies. So you need to exponentially increase your data size to see linearly many more word forms of the given word. So you do not see all the cases, even in a 5 million word or 5 million sentence pair parallel corpus. You need our biggest Czech corpus of 50 million sentence pairs to see all the morphological variants of the word češky. And actually, if you consider the linguistic annotation of those, there is this vocative case, which is used to address people or things. And of course, it hardly ever happens that someone will address the kneecaps. Oh, my kneecaps, what have you done to me again? That doesn't happen even in a 50 million corpus, right? So even though the word form matches with other cases, linguistically speaking, you would have a trouble there. Yeah. So the lesson to learn from this is that you need to study the phenomena behind your language, and this is where linguists are helpful. They will tell you which phenomena are productive, and productive phenomena will definitely mean that there is this greed for data if you are not modeling the phenomenon through like full linguistic generation rules for that phenomenon. What we did to address this in Czech is the trick that I called reverse self-training. And this is something which we proposed and evaluated in 2011. The idea is that you rely on the difference in morphological richness between the source and target languages. So if our small corpus, which is parallel, contains the word cat, exemplified in 2 sentences: a cat chased, so kočka honila, a cat was chasing something, and I saw a cat. In Czech, these 2 occurrences of the word cat are actually in different cases. So you are seeing the word in its 2 different forms. But what can happen to you in practice is that you get some input, and this input will still require some additional word form that you have not seen in your parallel corpus. And the standard phrase-based system will be totally screwed. And so is this any other language model if it's not incidentally modeling the morphological richness. So this sentence, četl jsem o kočce, is about a cat, but I am not able to translate it. So what we proposed was to use a reverse translation and to back it off by lemmas. So in Czech, we had this lemmatization tool, which converted all the cases of kočka, kočku, kočce into the lemma, kočka. And then you notice that this kočka is the same. So you can easily translate, and you learn to translate kočka to a cat, even though you didn't know the form at the beginning, right? So if you translate from a morphologically rich language backed off by lemma, so you forget the details of that language, into the morphologically less rich language, such as English, you actually happen to end up with a correct translation. I read about a cat. So this is a new synthetic sentence pair. And this synthetic sentence pair illustrates that the word cat can also be translated at this form, which was previously unknown. It's unknown form of a known word. The word is known because you knew the lemma, but the form was unknown. And you learn this form in the context, which is relevant for that, the prepositions here, they disambiguate, they indicate the case that needs to be chosen here. So this is the reverse self-rating approach, and of course the backoff has to be specific for the difference between the two languages. For other languages such as Turkish or German, you would need to split the words or separate and ignore the Turkish agglutinative morphology. But I think that this backoff strategy is part of the big contribution that back translation has on neural MT. So you now know that you cannot possibly train a good NMT system if you do not use some large target side monolingual data and apply back translation. And part of the gains comes from the fact that you actually use the additional data. But I believe that part of the gains also comes from this reverse self-training that we discovered several years before that. And measured with phrase-based MT, there is this known improvement as your language model grows, that your translation quality will grow. But if you use the language model data not only for the language model, but you also use it with this reverse self-training trick in the translation model, then you get like double the gain. So that's the good message. The bad message is that the gains from the additional the forms very quickly decrease. So if you have like 2 million of sentence pairs, then you will not see much difference measured by blast score, but that does not invalidate the original motivating observation here, that your system will not be able to confidently translate some rare forms of words. Yeah, so that was one particular trick relating to languages and noticing how they differ in linguistically productive phenomena, and benefiting from this by backing off in a way which the parallel data can then like help you to resolve and help you to learn new knowledge which was not available in your small corpus beforehand. So that's one interesting thing which I think you can mimic in your situations. And then another trick I would like to talk about is the transformer training trick by Martin Poppel. So I'll start with a summary of our English-to-Czech transformer based setup that we were like pushing for a number of years, and we were focusing on English-to-Czech for many years. For success, you need large, clean, and high quality training data. And back translation of monolingual data is very important, because otherwise the monolingual data like is not used by the system. It's also important to sub-process words or tokens to subword units. And this is very known these days. I forgot the term under which it appears today, but the different large language models are pre-trained with some subword units. And if these subword units are based only on one language, such as English, they will create very long sequences in non-Latin script languages, and that can very harshly impact the performance. And then transformer model is good because of its speed of training, and therefore it can process lots of data. And I would just to highlight that for low resource, you must not use the default settings. You should double check that the model size is in line with your training data. And then there are some like technical tricks. You ensemble or average the models. And the extra trick that we or Martin Poppel discovered was this block back translation. So what you normally do is that you have your authentic data, your parallel corpus, and you have the synthetic data, which is the monolingual data that you translate back to the source language. The normal approach is to mix these two sources of the data, and that this blue line here is what you get with this norm mixing. If these data collections come from kind of different domains, or if, as was the case for the English-to-Czech parallel data, if they primarily come from English and are translated to Czech, so the English-Czech authentic data illustrates translationese, so the language which translators produce, and it is in the target language, it is Czech, but it somehow still contains signs or properties of English. It's called translationese then. So if you have this translationese style of data versus the genuine Czech data, then it actually pays off to mix the synthetic and authentic data, not by fully shuffling the corpus, as the blue line does, but by first training on authentic data and then switching to the synthetic data for a while, and then switching back to the authentic data, and then switching to synthetic and switching to authentic, and so on. So train in blocks. And the reason why we think that this helps is that this has something to do with like the neural network optimization, trained on a particular domain, which is, it's all English to Czech, but some of the Czech is genuine Czech and some of the Czech is translationese Czech. So by training on these two different domains, it's like optimizing populations on two islands, and then you like you grow on one island, and then you move the population in the genetic algorithm sense. You move with the model to the other island where other like properties are more important, and you train there again. So the ways optimize again for the other island, and then you move back to the first one. So you optimize the weights. And along the checkpoints, you have some models which are good for translationese-like translation, and you have some other models which are good for genuine-like translations, right? And then you average, you combine the checkpoints along this crazily jumping training. And because this crazily jumping training is crazily jumping because of two domains, you will identify the best balance between these domains. And this is what will give you the best performance overall, right? So with this trick, in 2018, we were able to significantly surpass the translation quality of humans. And I would like to highlight that in that year, there was still a flaw in the evaluation. And the flaw was that machine translation was translating individual sentences, individual segments, and humans were translating whole documents. And the evaluation was done on individual segments. So machine translation operated in the same regime as the evaluators, and that gave it a benefit compared to humans. Put differently, in simpler words, if you are translating a sentence out of context, you will structure it in some way. If you're translating the sentence in the context of the full article, you will structure it differently. And then in the evaluation, if you're evaluating individual sentences out of context, the sentence that was translated out of context will sound better. But if you then apply this system and translate within the full document context and evaluate within the full document context, you will realize that the sentence doesn't fit well with the rest. So the evaluation has to be done exactly the same way as your final application will be. And if your evaluation is more related in structure to one of the competitors, that competitor, here the MT system, will have a benefit compared to the other systems, such as human translators. We re-evaluated it, and we found out, and that gave us this Nature Communications paper, we found out that humans indeed did more errors. So even considering the context, the transformer trained with the block back translation was better than humans. So it seems like we have reached the human translation quality. And there is another exercise that we did evaluating audit reports. And according to the GCSE style of scoring. Yes, the best system was on par with humans, or in one category, the spelling and morphology, it was even significantly better than humans. So has machine translation reached its goal? To translate means to preserve the meaning of the sentence, but NMT is not handling any meaning, or we have not discussed that at all. So it's just trained on millions of documents. You would need 50 years, 8 hours a day without weekends to read the training data that we have for our best system. So do these systems actually learn to understand in some way? Here's a first example. It is machine translation using that superhuman system from English into Czech. This is my English legalese. I translated something to English, and then I was translating it back to Czech with the system. So it reads as a legalese, supplement number 1 to the agreement of the sublease. I don't want to read that full. Here is the machine translation of that. Dodatek číslo 1 ke smlouvě. Again, superficially looks great. Legalese in Czech. If you look more carefully, you will notice that it says that the two parties are nájemce and nájemce. So both parties of this agreement are labeled with the same Czech word. So this is a superhuman translation, but it's totally useless for the purpose because it says that in this agreement, the tenant and the tenant have agreed to do something about the flat, about the apartment. Yeah, so this is a superhuman translation which makes totally useless outputs. Here is another example. This mama mele maso, mom is mincing meat, is the sentence that every Czech pupil reads in their first reading book when they're learning to read at the age of 6. And if we give this sentence to Google Translate, in the form it appears in the books, it translates it well. But if we turn it into a question, it suddenly is out of the training data domain, and it translates the question as meat grinds mum or meat mum grinds. If you do this with a different system such as Bing translator, mom's eating meat, again badly, mom's meat or mom's meat grinds, this is all bad translations. So very simple sentence known to 6-year-olds, and still the systems don't get it right. Our system was slightly better. Mom grinds meat. Does mom grind meat? Meat mom's grinding. So if there was a comma, I think that would be perfect translation. But also in yet another word order, mele mama maso, it will translate badly. Does mom have meat? So the systems don't understand the very basic the Czech sentence as soon as you change it into a question and shuffle the word a little. Is GPT any better? So there is the GPT-4o, the best model on Earth to this moment. And if you ask it to translate to English these sentences, it will say, "Mom is eating meat." Is mom eating meat? Is the meat being eaten by mom? So it totally disregards the concept of grinding. It swaps it for a different verb. So it doesn't understand Czech either. So now let me move on to the caveats on evaluation with working with neural networks. So one lesson which I label kindergarten lesson is this request: please test on unseen data. This is absolutely vital. And also you should read our colleague's paper on this. It's called Leak, Cheat, and Repeat. It has been published and won the best paper award at EACL this year. So Simone Baloku, Leak, Cheat, and others, Leak, Cheat, and Repeat. Definitely read this to avoid repeating such mistakes in your evaluation. The thing is that normally there is this train dev test approach of science. You have some training data, and if you want to test this quality of the system that you are developing, whatever it is, translation or something else, if you want to test it and anticipate its quality in new conditions, like in new on new inputs, you need to create the test set so that you remove the sentences. So see, the red colored sentences that form the test set actually disappear from your training data. And if you do it at the level of sentences, there is still quite a big risk that some important information is available in remaining sentences of the document. So, for example, a specific term can be translated and will be translated in other sentences of the document. And when seeing the same document, the system actually has an advantage by knowing the terminology from the remaining sentences in the document. So it's actually safer to create the test set by removing full documents, right? So this red document has been removed from this. But these days, we have models that are accessible from like through API only, and you do not know what they were trained on. So how would you possibly extract some test set instances from that if you don't have access to the data? So there is this idea of canary strings. If you're familiar with the Big Bench data set, it contains a canary string, and that's the string 26, B5, C6, and so on. And all the good players who train their models should avoid training on anything that mentions this canary string. I don't think that this solves the situation at all, because the original sentences could have appeared elsewhere by copy or whatever without that that canary string. And also these benchmarks often come from existing other data sets, which were published previously, and they, of course, they were published without the canary strings. So the canary strings are a helper, but definitely not a solution. And the problem is actually even worse. So imagine that the whole internet is the training set. So when everything is in from the internet is being downloaded and used to train these models, you cannot download your test set from anywhere. You have to create it from scratch. Otherwise, it's absolutely sure that it has been included in the training data. And then the problem comes that even great minds think alike. So if you think that you are creating from scratch some totally new instance, a difficult question for the model, you should actually first Google for it. And I bet that you will very easily find a related question that some clever mind has already asked before you. So you cannot be sure that your test set is novel until you like strive hard and create it novel and search the internet whether someone else has accidentally had the same idea before you. So I relate this to the situation to the goal of reaching the speed of light. In theory, it is possible, but it is getting more and more expensive as your speed grows. So what we are after is actually testing for generalization, but that's hard to do. So with that, I'm again moving to yet another part of my talk. And here I would like to highlight the unexpected lack of generalization and other caveats on, I would highlight other caveats on evaluation. So we figured out that transformers, and this was maybe not transformer yet, this was maybe attention-based recurrent network, but transform behaves transform behaves the same way as you will see on subsequent slides as well. We figured out we've spotted this problem of learn length overfitting when we were exploring curriculum learning. So we had this baseline of shuffled corpus, and this is what happens if you train on that shuffled corpus. And we said, okay, what if we trained first on easy sentences, and then we were gradually adding more complex sentences? Maybe with this curriculum, the model would understand Czech sentence structure better, and then learn to translate better. When we sorted the sentences, well, as you would sort them directly, like from the shortest to the longest, because of some repetition of the data in the corpus of the very simple sentences, which are very frequent and appear in many documents, the model did not start to learn at all. Like it only memorized the easy sentences, and then it didn't get the structure of sentences at all. So only at the very end of the training, it somewhat worked. So you cannot sort the corpus by length if you want to go from easy to complex sentences, because it will not learn. If you are clever, if you organize the sentences into boxes and first train on the box of short sentences up to 10 words, and then up to 5 words, up to 10 words, up to 17 words, and so on, then you can improve. And you actually see some little improvement, but at the end of your corpus, you do not know how to continue. With the shuffled corpus, you can keep training with the shuffled version. But here, should you continue with the shuffled one, or should you start again from scratch with the short sentences? We tried a crazy thing. We tried this corpus of these buckets backwards. So we first trained on the very long sentences, and we were gradually forbidding the long sentences until to the point where we allowed only sentences of 5 words. And what we saw here was that the model's output quality was totally decreasing. And the reason was that the model was unlearning to produce long sentences. This is the experiment refined further. And here it's with transformer. And we see that a model trained on sentences of all lengths translates the best across the board. But when you train a model such as this one trained in 40, this model trained in 40 performs best on sentences of length 40 to 50. And it decreases for all other sentence length, and same for all other things. This is yeah, let me skip that. So the lesson to learn from this is that the transform model is surprisingly overfitting towards the sentence length. It is producing the sentences of length seen at the training time in the most recent batches, and not not related to the input length of the sentence. It cannot extrapolate. That's not a surprising thing. It cannot translate longer sentences than it saw, but it also cannot translate shorter sentences than it saw. And very interestingly, it is not even able to interpolate. So if you train on a special corpus which has sentences 10 to 20 and 40 to 50 tokens, then when you ask the model to translate sentences 50 tokens long, it will not produce a sentence 30 tokens long, the mid-range. It will either produce a short one or a long one. So it overfits to this bimodal distribution. So it's unable even to interpolate the sentence length. And the reason is that the probability of end of sentence token is estimated by this plot. And there is 0 probability of emitting end of sentence around 30 tokens, because none of the training examples has shown that. So that is a very surprising inability to generalize. It can be useful. So here we have an example of like summarization for free. We have an input sentence of 30 words. The company does not collect its mail and it has closed its official headquarters in Žižkov more than 6 years ago. And if we translate this sentence to Czech, which is then glossed in English for you back. If you translate this sentence to Czech with a model which was trained only on sentences 10 tokens long, it will produce a 10 tokens long sentence. Společnost nezbírá poštu a zavřela oficiální sídlo. The company does not gather mail and close official headquarters. So we get a summarization model for free. If we translate it with the model for 30 words, it will be correctly translated more or less word for word or well. And it can also, the model can also be used as an expansion model, but you expand too much by asking for the double the length. So the model trained to produce 60 tokens as the output will say, the company does not pick up mail and close its official headquarters in Žižkov more than 6 years ago. In Žižkov, the company does not collect mail and closes up official headquarters in Žižkov more than 6 years ago. Yeah. So it repeats some of the content to match the desired, supposedly desired sentence length. So that's the inability of the transform model to generalize. So now, if there are still no questions, and I hope that you are still listening to me, if there are no questions, then I'll move on to another part, and that's caveats on interpreting results. So I see wishful thinking as a serious risk to research. So I think that progress in science and society relies on the reuse of ideas. So reproducibility is, of course, a key requirement for this progress. If you want to reuse something, you have to be able to reproduce the experiments. What I maintain is that even honest research can mislead others if it's complemented with wrong explanations. If you have a method which gives you some gains, but you attribute it to a to a bad reason, then this reason will be the thing that people will read in your paper, and they will use your method for that reason. But if the reason does not match the setting, then the users will not see the gains. So wrongly explained gains cannot be reproduced outside the very same setting than the original paper used. And wrong interpretations can lead to whole fields being built on shifting sands. So for that reason, we need to understand why we saw the improvements. It's not sufficient to see an improvement, but you need to explain it, and you need to explain it correctly. And I have two examples of some bad explanation. So one example is this training a transformer to not only translate, but also to parse the source sentence. So I assume that many of you know the transformer structure. It has 6 layers of encoder, then also 6 layers within the decoder, and it is producing the output sentence one word at a time. And when the input sentence is being processed, there are these self-attention heads across these 6 layers. And the self-attention head is formally very similar to the parse matrix, the parsing matrix, which represents the source sentence syntax. I said it's formally similar because for every token, you just say who is the important token, which other token is important for this one. So this can be used to indicate the governor in the dependency representation of that sentence. So what we did, we trained the transformer not only to translate, but also to indicate the governor for each source token using one of its attention heads. And we saw an improvement in blast score compared to the baseline when we requested this parse information to be available at layer 2, right? And that was the best performance. If we were curious about the best translation, best parsing quality, it would be better to wait and use the head from some deeper layer, specifically the second to last layer. And so we saw this as a great improvement. The message here would be source syntax helps machine translation. Train neural machine translation in a multitask setting. Train the model to translate and also parse your source sentence. I was experienced enough and like fussy enough, so that I asked a complementary question. What if we train the model to predict linear tree? Linear tree is no syntax. It totally disregards the syntax of the sentence. It says that every token is dependent on its immediately preceding word. That's totally bad. Such a syntactic, mock syntactic parse, when used as the requirement for the transformer head to predict, helps even more than using the genuine syntax here, right? So of course it's very easy for the transformer to predict this linear tree, but also the translation quality improves more. So the correct conclusion from this experiment is not source syntax helps neural MT. The correct conclusion is some constraining of the transformer head to make it a bistochastic matrix so that there is one in every column and row is helpful. So it's not the clever linguistic information at all. Here's another example of a published paper. Colleagues in Edinburgh have had success in 2017. They were using target syntax, and what they were doing is they were training the neural MT system not only to translate the source sentence into target, but also to predict the target side syntax using some syntactic tags. These are very complex, it's called CCG, combinatory categorical grammar tags. These indicate what syntactic role does the next word in the sentence occupy, and essentially you can reconstruct the syntactic tree from these tags. So they trained the model like this to produce double the length of sentences, and they saw an improvement. Well, we did some study of this again, and we tried using not only the correct CCG tags for the exercise, which they do help, yes, but we also tried random tags. So instead of this complex structure, we just said, okay, make any prediction there, like any tag. We shuffled the tags there, and we saw that this helps equally well compared to the baseline. So the actual reason for this gain here is not the clever target side syntax, but it's double the length of the output, because double the length of the output means that the model has kind of double the time, to twice as many layers, to consider what should be the token to produce for translation. Yeah, that's where the gain comes from, not from predicting the syntax. So another misconception that I would like to highlight is this idea of transfer learning. Transfer learning is something that you have a big corpus, such as Czech to English, those 50 million sentence pairs, and you have some target language of interest, Estonian into English, that is much smaller. And you would like to reuse this corpus to get the best possible quality for Estonian to English. So you first have to create the vocabulary so that it is balanced. I hinted on this previously. And then you train on the parent corpus and continue training on the child corpus. So let me go directly to the child model in Estonian. And we have experimented with 3 different parents when translating from English into Estonian. We first use the related language of Finnish. So Finnish from English, we trained on that for a while, and then we switched to Estonian to English and evaluated on Estonian to English. The Finnish English corpus is 3.5 bigger than the Estonian English corpus. And yes, Finnish is a related language. It helps compared to the baseline. We see 2.7 BLES score points improvement. Interestingly, we see a bigger improvement from Russian, and we see the biggest improvement from Czech. Czech is written in the same Latin script, but it's totally unrelated Slovak language, not an Ugro-Finnic one. And Russian is like geographically collocated language to Estonian, but it's totally unrelated linguistically, and also it is written in a different script. It is written in Cyrillic and not in Latin. So the conclusion from this is that it is the biggest corpus that helps most as the parent. So the transfer learning is helpful, but if you would attribute it to the language similarity, you would be attributing it to the wrong reason. It is not the language similarity. It is the size of the source of the parent corpus which helps most. Yeah. So I suggest that well, maybe still we still have the time to talk about these emergent properties of language models, and again warn about some misconceptions here. So I'm sure you know Word2Vec, and Word2Vec documents that train on just language modeling, the specific one where you like predict the neighbors of a word. The model maps related words to similar areas, and you can even consider vector differences to identify relations of words. So if you consider the difference between the words representation of king and queen, that will be the same as the difference between man and woman. So the difference is also indicated something. And this was tested on the in the original paper by Tomáš Mikolov. It was tested on this test set using 2 types of questions. One was this semantic question, and one of this like syntactic set of questions. It's actually morphosyntactic. It's related to morphology. The semantic questions test whether the model learns to identify capitals and their countries, and capitals well, what is that? Capital and countries, and capital and this is some limited set, and this is from the whole world, I guess. Then currency and a country, and then presence of a state in presence of a city in a state, and also some family relationships. So these 5 semantic questions, these were like reasonably well answered by the model, and the syntactic questions are morphological relationships between words, like opposites, aware, unaware, comparative, bad, worse, superlative, bad, worst, or past tense, dancing, danced, plural, banana, bananas, right? So if you look at the test set of Tomáš Mikolov, it is 8,000, which is a lot of semantic questions, and 10,000 syntactic questions. That sounds as good. And if you look at some of these outputs, you would say, yes, the accuracy is quite good. The actual paper says that the exact match is only 60%. So you need to read the fine print as well. Okay, what we see as a bigger problem is the non-representativity of this test set. When we examine this test set 3 years after that, we notice that the semantic questions actually cover only 3 question types. It's the relation between country and city. Some of them are between world cities and world countries, and some are subset of that. Then between country and currency, and then also something which is called like the family, and it's only the masculine versus feminine transformation, right? So yes, there are papers such as Yekaterina Vilomova's paper, which tests many more relations, but the original test set is limited to just these 3 types. And the syntactic questions they also seem as like big test set, but they actually start only from 313 distinct word pairs, and then they are combined with each other so that you get this large number of pairs in the test set. And of these 13 word pairs, actually 286 are formed regularly. Like there's no point in using this clever model to do that. So we then quantified what effect this has by creating our own test set. You can look at our paper from 2016, and the original Word2Vec, as it was released, reaches the 62% accuracy on Tomáš Mikolov's test set, but it's only 43% of accuracy on our much richer test set, where we were covering a wider range of phenomena for the morphosyntactic questions. When we try to retrain Word2Vec ourselves, we were not as good as Tomáš Mikolov, so we only reached 42%, and that's we don't know where the improvement comes from, but this is how we trained it. Maybe the implementation was different, some bug or whatever, but evaluating this implementation on our test set gives us only 9% of accuracy. So our test set is like harsher, and it reveals that this model does not work at all. We came up with an improvement of Word2Vec, which we call subgram, and the subgram makes a big improvement on our test set. Still, it is like 22% in total, so not a great score. And it's interesting to notice that using Tomáš Mikolov's test set, there is no gain visible. So this very like non-representative test set does not help you to identify that the model is actually better. Yeah, the whole point of this of the original paper by Tomáš Mikolov is to highlight the emergent properties, the relation between words. So I don't want to deny that improvement or that advancement. That's something amazing that the model automatically learns these relations between words. It's just not as good as we think, and also the practical utility of this is limited, because if you write manually just 9 rules, you will get 70% of accuracy on Tomáš Mikolov test set and 66% of accuracy on our harder test set, right? So this is to highlight that using explicit linguistic knowledge is very often the best thing. So aside from collecting data, yes, do spend some time also to writing 9 linguistic rules, and then you will have a nice lemmatizer which you can use in the back translation approach or the reverse self-training approach, for example, and it will move you much further than relying on fully unsupervised systems. The emergent properties are interesting, but for practical use, you are probably better off by focusing on the frequent cases and writing few rules for that. There is also some ultimate evaluation, which in research is the number of citations. So our subgram is very similar idea as this Boyanovsky paper in 2017 published. And there is some difference. The 2 papers were developed in the same time. We developed it and submitted to a classical conference with closed like review process. We submitted it there on March 22. In July 15, the Boyanovsky paper appeared on Archive, and our paper appeared only in September after that, because of the review process and because of the low awareness of this conference, and because of this delay as well, our paper got to a certain point only 13 citations, whereas Piotr Boyanovsky's paper appeared in Tackled some years after that, and it received 10,000 citations. So you also should optimize to the venue where you're publishing, and you should publish your results quickly if you have the same good idea. There is also one more difference that I need to admit. We didn't release any code for the same ideas as Piotr Boyanovsky, and the code that we had was not fast at all. But the Boyanovsky paper is the fastest paper, so that's the difference here. So with this, I'm coming to the end of my talk, and I would like to highlight that machine translation, even for language which is spoken only by 10 million of people, can reach very good quality. So we were relying or we were building up on all the data that we accumulated for statistical machine translation since 2006 or even earlier. The datasets, of course, contain all the text as well. We used big GPUs, and we used lots of training tricks, and we spent some weeks of training time. So in 2018, we were able to reach average quality comparable to sloppy humans. This is a great achievement in like a decade and 2 years or so. Yet no understanding is present in the models, and that holds also for the current large language models, as you saw. And sometimes these horrible errors appear, and there is a surprising lack of generalization that people do not realize. Then another lesson to remember is that with neural networks, the intuition why something works is often wrong. You definitely need to use trivial baselines and contrastive experiments, such as random baselines or like random inputs for the very, very same network structure to exclude misinterpretations. And I would also like to highlight that we grossly underestimate the similarity of training and test data. So it is natural that sentences appear like repeatedly, and it's natural that people talk about the same thing in the training data and the test sets. But you should be very careful when you are claiming any generalization or emergence, because it often comes from some form of data leakage. So have a look at the leak, cheat, and repeat paper. So if at all possible, do train from scratch and use a carefully prepared test set, which needs to be representative, diverse, and independent from your training data. So if you want to read more about some of the misconceptions that I highlighted here, I suggest or recommend our book, The Reality of Multilingual Machine Translation, which is available online. And we highlight these and further errors. And To answer the question from the title of my talk, to have your language covered by NLP tools, I suggest these steps. So you should collect the data and you should look at them, and you should really make sure that you are able to understand what is in the data, and you should have a picky eye and focus on the details, normalize and so on. You should consider distributions of phenomena that are relevant for your task. This is related to the morphological richness and the endless zip flow tail. Linguists will focus on the
Excuse me, sir.
Yep.
Sir, we have a 5 minute left.
Yes,
So
that's
could
for
you
the
please
questions. I'm
summarize
stopping.
your remaining points?
Yeah, that's it.
Yeah,
I'm
thank
there
you,
at
sir.
the very end. Linguists focus on the exceptions. Sometimes this is amusing, and definitely this is inspirational for what you need to generalize in your models. Engineers will focus on frequency and produce systems that are useful in practice. Then you create shared tasks so that others help you, but you should evaluate them ideally really yourself and manually so that you understand where the field is moving. So again, read the outputs of your systems, and don't fall in some thoughtless annual loop of these shared tasks, just looking at the numbers of some metrics. Make progress step by step in your understanding. That is the key point. And be extremely careful about explaining the results, why the network has given you this gain. You should not trust even your own good results until you explain them. So that's it. Thank you. And if there are any questions, I'm happy to answer them.
Yeah, any questions? US?
Can I ask a question?
Yeah. Yes, please do.
Yeah. So while training your MT systems, what matrices do you generally use for evaluation?
Metrics, or evaluation scores. Yeah, so this is a totally this is a story on its own. To be honest, I still look at BLAS scores because I know the ballpark figures, like what could be a good BLAS score, what could be a bad BLAS score. But that's because I have long-term experience with that. And then I know I also have quite some publications on the limitations of BLAS score. So I know when the BLAS score is deceiving. And I use this to my advantage as well. So I see that the large language models obtain low BLAS scores, even though they have good translation outputs. And I see this as an indication that they produce more natural rather than translationese like output, right? And BLAS score is what measures translationese because it measures the similarity between the reference and the candidate in a very shallow way. So what we trust more, of course, is COMET, and then I still use CHRF, which I pronounce HRF. It's nicer for me to read like that by Maja Popovic, which is more robust to language like independence, but it's still string based. Definitely, and that's the most important point, I do look at the outputs. So I always use, even if it's just 50 sentences, I always use manual evaluation. I hope I answered your question.
Yes, sir. And in manual evaluation, you use adequacy and fluency.
Actually, I often use just pairwise annotation. So for this, I'll maybe switch to this web browser. I have this Quick Judge tool. It's very simple. Like Quick Judge now lives on GitHub. It is a very simple tool which you feed with input, referent, and 2 candidate outputs, or it's actually arbitrary, any number of outputs. And it will create some annotation file, which is like this. It will shuffle the systems for you. And I do like a relative comparison. And here before these candidate sentences, I just write any comment, right? So I, for example, label them with 2 stars or some stars and some error labels, right? And then I use Quick Judge to collect the annotations, so it will unshuffle it for me, and I very quickly interpret this that the system out B got 2 times 2 stars and is therefore a winner. So this is the relative scoring that I use for quick assessment, right? So it's simpler, and it's always targeted for the phenomenon that I'm focusing on. And otherwise, I'm following and contributing to the WMT evaluation for the whole development of evaluation metrics.
And how is hallucination handled in NMT models?
It's not. Yeah.
Thank you.
Yeah. So yeah. Was there another question?
Yeah, another question in chat box. You can take that one. The 9 rules you discussed about which improve performance are those laws of grammar of some derived ones. Could you explain more about that?
Yeah, so the thing is that the test set is simply non-representative, right? The syntactic, or I would call it morphological questions, are constructed from a very small number of word pairs, and most of these word pairs are formed regularly, such as illustrated here, decrease, decreases, dancing, dance, banana, bananas. So the rules are like, un to create the opposite, ly to create the adverb, s to create the plural, and yeah, so that's it. So these rules are kind of inspired by what you would learn in the first year of learning English from your teacher, like that adverbs are constructed by by attaching the ly. So we have the rules, I think, listed in the paper. It's nothing fancy.
Okay, thank you. And another question from Joya. Are you there? Can I ask the question?
Yes, sir.
Yeah.
Yes, sir. Actually, I'm currently working on Odia, which is a low resource language.
Mm-hmm.
So there's not enough data available. So to create more training data, we tried to augment the data,
Mm-hmm.
and for that we tried back translation.
Yes.
However, the data, like the input data and the output data, varied a lot.
Mm-hmm.
When English was getting translated to Odia, the translations were very incorrect. Whichever model we've tried, and we've even tried embeddings, but it does not work properly. So, what would you suggest for this?
Yeah, so this is I would need to know more about your setup. Are you translating from English? Are you mainly focusing on translation from English into Odia or from Odia into English?
We're translating from English to Odia.
Yeah, so in that case, you need to collect monolingual text in Odia, of course, and translate these from Odia to English. This
Yeah.
back translation system, does this one work reasonably well for you or not?
The translations are very incorrect, and since we're translating manually, because most of the translations were incorrect when we were doing it online, so we try to translate it manually. So it's been a very, like, it's taking a lot of time. So currently we have a data of like, if we have a data of approximately 3 to 4,000, we're working on sentiment analysis. So most,
Mm-hmm.
and we're using review data. So most of the data is positive. So for
Mm-hmm.
negative data, we're trying to like create a balance. So to
Mm-hmm.
increase
Yeah,
the amount
yeah.
of negative data, we'll have to augment the data. But whenever we're trying to translate it, the translations are very incorrect. Like the words are totally different from what they actually mean.
Yeah, so I think that your situation is further complicated by the fact that your downstream task is not the translation itself, but something else, sentiment analysis.
Yes.
And I would definitely compare it with solving the task itself in English, right? So that you would use standard English sentiment and classifiers, and you would translate your inputs and run the task in English. This already is kind of like a back translation or move to the better covered language. And I think that this way you would be better off. So I would focus on collect genuine reviews, as large collection of Odia reviews as possible, translate this to English and run sentiment analysis on this, and then manually revise the sentiment assigned by that. So I would like extend the extend the range of what you do back translation for to include also your downstream task of sentiment analysis and not focus on the translation as such. Because translating or creating a translation system from English into Odia will be difficult, and synthesizing data by taking bad reviews in English, if I understood correctly, this is what you're doing, and translating these like negative English reviews into Odia, that will be much harder to achieve than locating negative Odia examples, translating them to English, and finding and selecting the negative ones.
Yeah, but the thing is that a lot of people don't prefer to write reviews in Odia. Even if the words are Odia, they write it in English.
Mm-hmm.
So the like it's written in English, but the pronunciation are Odia words. So in that case, the models don't work appropriately on these.
That's strange. So you're saying that there is no genuine or a very, very small collection of genuine
It
Odia.
is very minimal. Yeah.
Yeah. Well, it's a hard situation. I would still try to search for more. Like it's, I would, yeah. Yeah, that's. I think that would. I think that would in the short term this would be the best strategy indeed. Like collecting data always helps if you want good.
Yeah.
And also in your final application, because you have your final application, you are expecting to receive Odia reviews. So create a system so that it is ready to accept Odia reviews, but internally it translates them to English and provides the assessment in English.
Okay. Thank you so much.
I have one
Can I
question.
add one thing over here?
Last question from Bayano Singhs.
Yes, sir.
Yeah.
Yeah, am I audible, sir?
Yes, yes.
Yes. So in neural network machine translation, we use BP for encoded. So
Yeah.
there's in BP like there's some type like sentence space, word space. There's some types are there. So which is kind of there's subword BP sentence space are also there, no sir. So which
Yeah,
one
yeah,
is
yeah,
the
so- yeah.
better for better? And one second question is like all our model evaluation we use automated blue score. So blue score we have to evaluate on the BP level or in the word level
Yeah,
for
well,
kind of presentation.
no, you should not use Blastcore. That's the um, well, in your papers, if you're asking about like what is the best strategy for having a paper accepted, definitely feel free to provide blast scores. They are good for you and good for old schoolers like me, but do add CHRF, do add Comet if it's at all available for your target language, and do add manual evaluation. That is absolutely critical, right? Without that, the paper should not be accepted. Like you should not trust blast scores. Yeah. And for the subwords, it really depends. It varies on the data. It depends on the data set and on your particular setup of the system. So we experimented not with the different implementations of subwords like the sentence piece versus word piece versus BPE, but we experimented with linguistically motivated and unmotivated approaches such as BPE, and the linguistically motivated were not better. But for the best performance, you should try all of those on a smaller scale and see which one of them performs best for you and use that one. And I would also strongly recommend to actually look at the tokenized version of your data. So read it yourself. Put yourself into the shoes of the model, because you will then. I don't want to locate the example right away. I have it somewhere in some other stack of my slides. But when you read the outputs of the subword tokenizer yourself, you will immediately realize which words kind of collapse together, and they should collapse together, and which words collapse together and they should not collapse together. So they should collapse together when you're separating, for example, the ending in a declination form, and they should not collapse together when they are mixing the meanings of two different things. So by looking at the outputs of the tokenizer, you are able to also qualitatively choose which of these subword methods has a better chance for unseen data. So this is like bringing in the linguist, and the linguist has the sense for the fine detail and for the endless tail of these fine details. And you want such a tokenization method which generalizes well across this long tail. And this is something that is difficult to measure by observing it on a test set, because the test set would have to be very, very long. It is easier to spot just by your eyes and your knowledge of the language.
Yeah. The second question was like, the evaluation should be done on the BPA level or the word level, sir?
It depends on the application. I don't think it matters. I think if you are comparing systems in a comparable way upfront, like if you're not making some error that one of the systems would be, but there are many ways in which you could do it badly. But if it's comparable setting, then the tendencies should be the same at the word level and subword level. It's the main message that I didn't say aloud today, but the main message is that you must not compare BLES scores across paper or any scores across paper. This is actually illustrated already in this table. Like if we trusted the Word2X score as it was released and evaluated by Tomáš Mikolov, we would have said, oh, we have no chance. Like we are 40% below that, and our clever method, the subgram method, has no chance. This 22 compared to 62. But first, by replicating and not trusting the score as such, we figured out, okay, our Word2X implementation is problematic. This is one thing that would need to be examined further. But also that the test set does not show the difference. So in short, comparing the numbers across papers, this is from the paper, this is our re-implementation of that, is a bad idea. What we should have done is we should have asked Tomáš Mikolov to give us his outputs and evaluate his outputs with our method. That way we don't have to re-implement his method, but we are still reliably evaluating it. And as soon as you are comparing actually the outputs, as soon as you have the outputs in your hand, it really doesn't matter whether the BLES score or the metric you uses this tokenization or that tokenization, because all the systems will be affected the same way. So don't copy numbers from papers, always re-evaluate and sometimes re-implement.
Thank you so much, sir.
Yeah. Welcome.
Thank you. So thank you, Dr. Andres. Very, very informative session, and definitely our student will may contact you for further details. Okay.
Yeah. I'll share the slides, of course, so we can then put them on the web as well. So
yes, definitely. And I will also contact you. I have some problems or doubts are there. Later, I will contact you. Okay. Thank you very much then.
Okay.
So, yeah.
Thank you.
The end of the meeting. Thank you. Thank you. Namaste.
Yeah. Namaste. So I'm trying to stop the screen sharing now.
Okay. Thank you very much.